All right, I wanted to continue working on Blender math because it's so much fun. And I call this Blunder through Blender because I spend a lazy Sunday afternoon on Mother's Day figuring out how to learn and thereby teach math, which was never taught to me all that well. And school turned me off to math, and Blender is helping me rekindle my love for math. It's a slow process because I'm very busy and I've got a job and a life like we all do, but math is so much fun that I want to be able to go to my grave uh, understanding it much better and really feeling and seeing its beauty. So Blender's going to help me doing that, and the way it's going to do that first is by going into the shader editor here and hitting the number 7 key and looking at this default cube from above and moving my material output and principled BSDF shader over to the right and adding to the left, adding a texture coordinate, because that's what we're going to do is we're going to put textures into this graph. And then, let me make sure this is on okay. It looks to be, it looks like Blender's all there. Using OBS Studio here. And then the next node that is crucial to add is a mapping. Actually, this is not crucial, but it's helpful because you can change the scale of the X, Y, and Z. Going to the object and connecting it to the vector, and then adding, and this is crucial, the separate X, Y, Z, or separate X, Y, and Z, make that a verb. Separate X, Y, and Z node, and those on the left and these on the right will then give us the output. So you wouldn't get much of anything when you just connect it like that, except a black and white line on the sphere. On the sphere, sphere, good for you. It's on the cube. But now we're going to manipulate that by using math. I guess that the black represents negative numbers or 0, and then white is positive, I guess. So what I want to do is I want to try an equation that I'm going to grab from, and I'm going to grab it from where? From this equation set. I'm going to try to get this upside down parabola, which is going to be y equals 6x minus x squared. So let me do what I always do and add a grease pencil so I can, write some stuff in here. And I'll do a blank grease pencil, and then I will go into draw mode, and I'll remind myself what I'm doing, although I want to change that color. Lordy, that's an ugly color. I'm going to eliminate that, and I'm going to add to that let's do a blueprint grease pencil like that. Okay. So that light blue there. So what was it? Y equals, and then it was 6x, I think. Oops. Didn't mean to do that. Y equals, let me look over here, 6x minus x squared. So 6x minus x squared. And to use an equation like this in Blender math, you want to get everything over to 0. So we could say 0 equals 6x minus x squared minus y. Do that. And then we want to use the PEMDAS. Let me add some text here because sometimes writing with a mouse is really uncomfortable. So go back to object mode, and I'm going to add a text object and move it over and shrink it down and edit it. And then, so we're using PEMDAS, which is equals parentheses, then exponents, then multiplication, then division, then adding, and then subtraction. That's the order that we want to do it in. And I need to fix that. add, subtract. Okay, so that's the order of operations that you want to put into this. So when I go back to my cube and I go into my shader nodes, then in this shader node, I'm going to add a math node. And that math node is going to start with what's in parentheses. There isn't anything in parentheses. Start with exponents. So we have an x squared. So there's x coming in as the value, and we want to make it an exponent, which is a power relationship. And we want the exponent to be 2. And that is how x squared looks from the top. And then we want to take that x squared and we want to subtract it from 6x. So we will add Shift D and add this over and turn this into a subtraction. And from the subtract, we're going to subtract the x squared from 6x. So let's bring this down to here. Let's add another node here. So add a math node and bring it down here. And this has to be attached to x as well. And then that's going to be multiplied by 6. So multiply and put the value that it's multiplied by to be 6. And then we're going to take that multiplied 6x and we're going to subtract x squared from it. And then we need to subtract y. Now the thing about this is that this graph looking down, so looking down, if I went like this, we would have the z-axis going up and down and the x-axis going left and right. If I look at it like this, then it's the y-axis going left and right and the z-axis going up and down. And so you can flip it around, but from the top, the green is the y-axis, which in your Cartesian coordinate system in 2 dimensions was always on your graph paper in high school. That's going up and down, and then the red is the x-axis, and we are in the middle of those quadrants over here. So the y has to be referenced here, or the shader doesn't know where to graph these textures, where to put them. So we need to have a y, and the y is left unassigned so far. It's over here in the middle here. And so we're going to subtract y from all of this. So I'm going to add another math node, and you can just click on any one of them and hit Shift D, but you'll then have to change it. So this subtract node is going to be coming out of all of this, as if we'd put these in parentheses. So when I take y and I subtract, let me see, yeah, take all of that and subtract y, then it looks like that. Now, is that interesting? Let me see if I change the scales here. Aha, yes. So it's going to be deceptive if your scale is at 1 and you're like, well, I'm not seeing how that matches anything that I saw in my equation here. We're supposed to have a parabola that is negative, that starts at 3, 9 and goes down to 6, 0 on both sides. And you'd be, well, how does that work? And that's why I earlier said it's critical to put in mapping. Well, it's not critical, but because it's still there, but you can't see it. So here you bring your scale, and if we bring our scale up to 10 here and 10 on y, then we get a negative parabola. So that's pretty cool. We can move it, of course, using this part of the mapping there if we want to. But it actually shouldn't be moved, because look at where this box, and let me see if I can, if I go there, you can't really see the, I can't see the texture because this isn't transparent, but we want to make sure that this part here is at 3, 9, I guess. Let's look at that. Yeah, there's 3, 9. So x of 3 and y of 9, 1, 2, 3, there's x right there, counting those little squares, and then 9 to get up there. 1, 2, 3, oops, no, we're coming from the x-axis, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it does bear out. It's at 3, 9, and then it crosses on both sides at 0. That's the center right there. Right? I mean, can't really see it in here, but that is indeed the center. That's 0 in the x and y, and then over here it is 1, 2, 3, 4, 5, 6, just as they suggested here. So 6, 0 in the x and the y. So that's pretty exciting that you can get these figures by going and making this math work. Now, once I have an equation like that, let me save this, save as, and go to beautiful equations.blend. And where do I put that? I'll put that in my 3D objects, save it there. Once I have that, of course, black and white is so passé, it is so retro, so 1950s. It is interesting to come in here and add a mix node. Has it a mix color node? Yeah. Add a mix node and then bring that figure into the factor and then change the colors. See what that does. Do a darn thing. Maybe I should put the mix node over here. This one always confuses me. Let me delete that. And let's delete the BSDF shader. Let's go to here. Now we get our parabola. Let's add again a mix color. And bring this to the factor and then change, there we go. So now we can have some fun by changing different colors. And that's always pretty. So yay for that. There's a lot of stuff we can do, but that is much more visually compelling in there. All right, so we save this again. Now what if we want to create a new scene, but we want to change those parameters? So I'm going to go here and go to a new scene. Should I copy the settings? Let's see. Didn't do much. And then let me see if I go back to this first scene. This scene is going to be called y equals, no, I'm not going to call it that. I'm going to call it negative parabola, because I can always change the values. So I've got that, and let me go then to my new scene. And is there a way, let me see, to copy all of this and bring them over? I do Control C and I go to the new scene and paste it. No, it doesn't let me paste anything from there. What if I do duplicate? No, that's copy right there. And then go to the next one and then go to, nope, there's no pasting. Ain't gonna work like that. Duplicate is not going to work either. I don't think. Duplicate just puts it like that and then can't get out of that. So forget that. So forget the duplicate. How I copy that over, I haven't learned yet. You can always go and make a whole new scene, which is called full copy. But then I'm afraid if you change any parameter in one, and then you go to the other one and you change it, and the full copy is, yeah, it doesn't help us do anything. So, oops, we don't want a full copy. That's not good. Oh, we didn't do that. We're going to get out of, oh yeah, number one. I'm going to get rid of that. Just delete it like that. So I guess we'll just set up a whole new scene. It's always good practice to do anyway. So we're going to what? We're going to add a shader node. But the shader node ain't showing up there, and it's not showing up there because world line style. It's the shader editor. How do we make a new shader thing? Put in new shade. Use nodes. Okay. Does that help? Color. Let's do just a regular environment texture. No, it didn't do a darn thing. Isn't that interesting? So I ain't got nothing for this new scene. In here I have a slot with a material, and in here I have no slot. Add a, is there anything I can add? Layout, frame, script, vector, texture, shader. It's not letting me add anything. How bizarre. I never thought that would happen. So let's delete that scene. Now how am I going to make a new scene? What if I make a new scene? I will go to a linked copy. And then if I change this, does that affect my other one? Yeah, it sure does. And that's not what I want to do. So I don't want a linked copy. And I do want to do a new thing, but I want to have, I know why. Ha 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 ha. Hey, if you were paying any attention to this and didn't get bored and walked away, it's because there's no object in there. Without an object, it's empty space. How are you going to describe an empty object? That's weird. So yes, you have to add an object. So add a mesh cube. Bingo. All right. Now I can add a new shader. And I wonder if now if I can copy the shaders from here. Oh, let's try. So Control C to copy them, and then go over to the new scene, and then right click and no, let's paste. Ain't nothing going on there. But okay. There is just a possibility of recreating everything. So let's do that again. Texture coordinators, because that's good practice. Texture coordinate comes in. Hey, nothing happened. Why not? Come on. Add texture coordinate. Because I didn't click on new, and because I didn't click on new. All right, let's do that again. Add a texture coordinate. Boom. All right, good. Take the texture coordinate, add a mapping node. Good. Join them from object to vector. Add a separate XYZ node. Good. And connect those in, and then bing. And of course, what did we say earlier? It would be good to add always a mix color node. The fun of it, to make it pretty. Mix color. Bingo. And make this a factor. And then we can change the colors to weird things like pink and green. All right. So that is our cube so far. And now we're going to go and do another equation. And the other equation is going to be, well, that's just a parabola. It's the same thing. Just moving some of the, aha, let's try. Ooh, can we even do this? F of x equals -1. So f of x is usually considered the y value, but this is a limit. So I'm limited. I'm beyond until I study more. I'm out of my depth. But if this one here, horizontal asymptotes, if that f of x was considered the y, then we manipulated x minus 1. It's just that these are all limits and they're not fixed things. What somebody who really knows math would like, yeah, that's easy, working with polynomials, no problem. That's just a typical parabola. That's an inverted parabola. I wish I could do this more like a sine wave, but they're not using sine for this. They're using tangent lines. That is just mx, y equals mx plus b, so that's kind of boring. Let me look up something else that we can try. Let's do, there's 10 basic algebraic graphs that everybody kind of knows. So there's the quadratic polynomial, the cubic polynomial. Yeah, okay. Y equals x to the cubed, x cubed, x to the third. All right, let's try that one. That could be fun. So let's go here and let's say if we have to again add a grease pencil and go to drawing, and it's going to be y equals x. cubed. Let's try that one. Back to my cube, and go back to object mode, and then say, all right, great, y equals x cubed. That is the one that we're doing, right? Y equals x cubed, a simple polynomial. So let's take that, and let's go into the y equals x cubed. Oh yeah, we have to change it, we change it to 0 equals x cubed minus y. And because of PEMDAS rule, the power function, the exponent, comes first. So when we go back to our cube, we're going to add a math node and drop it in. And we're going to make that math node an exponent, or power. And we're going to make that 3 for the cubed. And we're going to say that x cubed is what it is. That's it. And in fact, I can come over here and I can change the label to x cubed so that I don't forget what I wanted that label to be. All right, and it's x cubed minus y. So we're going to now add another one. So I'll Shift D and duplicate this. And we're going to subtract that. We're going to subtract y from that. So we have subtract. And loading, there it is. Now it doesn't have much definition. One way to do that, I think they said that you add another math node, which is, and you make it a multiply. Yeah, and that defines it sharper. See, and I can, because then what's happening is that all of the values that look kind of misty foggy, that's because the texture nodes are saying that they are in between numbers, kind of. And when you multiply them, make them, it has a cutoff thing. It's sort of like a, what would you call it? It's like a clip. It's clipping. And so when you multiply it by a really big number, then you have greater definition of those numbers. So there it is, very pretty, y equals x cubed. And that one is the cubic polynomial graph. Now how do you get it to look like this one here? Goes to the origin and the 0.11. Well, I think it already does. But if we, again, want to scale it, see, scaling it will change things. So let's scale this by 2 and 2. We don't need to scale z because there is no z in this. Maybe scale it by 3. So scale really matters in these things. Now it looks a little bit more like what you saw over there. All right, so save that. Let's look for another basic algebraic thing. The graph of the line y equals x. Well, that's really, really boring. But we might as well have it. And let me show you something with that, because if I make a new scene, and this one was called, what was this called? This one called the cubic polynomial. So that's going to be cubic polynomial. And now we're going to make a new scene. And of course we have to add a cube. Add a cube. And then make a new texture for it. And once again add the texture coordinates, and then from the texture coordinate add a mapping node, and then from our mapping node add a separate XYZ. Click on it, separate XYZ. All right, and connect the object to the vector, and then the vector to the vector. And we also said that we always want to add, as part of our default setup, we want to add a mix color node so we can make things pretty. All right, so we've got that, and we're going to connect things. We're going to change the colors here. This time I'm going to use yellow and blue, and then connect to the factor. And there, that's our beginning. That's the beginning of our setup. Now we're going to do some math. So it's going to be y equals x. And so we're going to need two math nodes at least. So let's go math. And let's duplicate that math one. And y equals x is really, really simple, because it is actually going to be, if I write it out again, so always add a grease pencil, and then go to the draw mode and say y equals x, but you'd have to change it to 0 equals x minus y. Now with 0 equals x minus y, when we go and do this, we are going to then say, well, x is what we're starting with, and we're not doing anything, we're not adding or anything. We should probably do a multiply and multiply it by 1, so multiply it by itself, okay? And then say we have to subtract y from it. So here we go to a subtract, and we take what we want to subtract and put it under here. And lo and behold, we get that. Now, once again, oh, you know, I think this should be part of our default setup. We should always then put another multiply over here and then bring it up. Yeah, so we get rid of that. So that's going to be part of our default, and multiply at the end, so it gets really well defined. But yay for that. Not so fun though, because we can flip it around, and then we realize that this value here is actually the slope, m or a. So what we should do in all of these equations, with all these polynomials, and I guess quadratic equations, is we should always make sure that we're saying ax by, right? And then this becomes ax minus by. And then we should also put in another thing, which is c. That's how you write these polynomials. Because if you do that and you set up so that you always have an a and b integer that are multiplied by your coordinates, your xy coordinates, and you always then have a number that you can add or subtract, then you can play with it, and you'll have basically what we used to see in school as y equals mx plus b, the y intercept slope, point slope formula. And we're just writing it as 0 equals ax minus, ax, and then you're subtracting the y, but we can keep the b in here too, except we call it c. You don't want to use that b. It got very awkward, the slope being m and b being the y-intercept. Ick. I don't like it. I never liked it. And so I do want to add something here and make a new base color, make it red. And then I want to pick that base color and I'm going to say, get out of my face. It's going to be this instead. And it's also going to be, and let me pick my color here again, plus c minus by. So it could be that. This could be plus. That's the form that we want to do the point slope formula in. And that makes it much, much easier to manipulate and then really understand it. So I don't know why they're always confusing kids with all these different letter combinations without explaining why we put them there. Blender helps us to understand why we're putting these things there. So in our equation, we want to say that 0, which we don't ever put on here, equals ax, and the ax is this value here. This is our a, which you used to think of as m. This is our slope, the number, the value that goes in front of x. And then we have a subtracting a y, but before we subtract the y, let's get rid of this y for a second. Let's set up a multiply for y. So we're going to take this and shift D and take it there, bring y into it as a value. Now we have something to multiply y, and this one we can label as ax, and then this one we can label by, and then we can hook this up to the subtraction value. And now, of course, if you multiplied y, you're also affecting the slope. And they didn't tell you that back in the day, but they both affect the slope, and they can compete with one another, because if I'm making a slope of 4 over here, and you're like, okay, that's my slope. Wow, it's really steep. And then you say, yeah, but I'm multiplying the y by 4 as well, and then you might as well not have multiplied either of them. You get that slope is still 1. So that's really important, and then you can search algebra from that, and how, if you divided by 4, it would end up 1. So it's good to have that in there, and just know that you're usually setting this to 1 so that you can manipulate the slope with the slope and the point slope around. And then, of course, you have that c, which is the y-intercept, otherwise known as b over here. So if we want to put in c, it's an addition mode. Then we go Control, or rather Shift D, Shift D, put this there, and then make this an add node. And that c is the y-intercept. And you can see that if it's set to 0, then it goes right through the center where the y line and the x line meet. That's the y-intercept. But if you increase it, then you start bringing that y-intercept back and forward. But wasn't it, yeah. So here it's meeting at 7. It's just that it's negative. Here it's meeting at just roughly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right there. So negative 1 there, that would be at 10 where it meets. So that is your y-intercept, and so you can write it that way, or you can say c or y-intercept. And by labeling, you keep things much handier. It's easier to see. So yeah, manipulate the y-intercept, manipulate the slope, and you can have all sorts of great decisions that you make there. And I think what's really cool is that if you set the y-intercept to 0 right in the center, and you manipulate the slope, then you can get some interesting results, but you can also just move that whole graph over by deciding where that y-intercept is going to be. All right, so now that we've gotten this concept that you should be putting in these other variables in there, now when we go to do other graphs, we should observe that. So let's go back to our cubic polynomial, and we'd written here 0 equals x cubed minus y. Well, that means that this should have something that it multiplies by before we cube the x, or no, after we cube the x, because in the PEMDAS rule, exponents or powers take precedence. So let's take this and Shift D and duplicate it and change it to multiply, and then by changing it to multiply and saying that this is ax cubed. Then we can come in here into edit mode. Let me move this 0 over. Oh, I shouldn't have done that. Okay. Hit G and move this 0 over. And then take this and move the, oh, didn't need to do that. Sorry. U2. All right. Move this equal sign over. And let me go back into draw and say this is 0 because ax cubed minus by plus c. And then we can make sure that every equation that we have has that in its setup. So this was, I didn't give a good label for this. This one was the subtract for y. Oh, and this was just the multiply so that it's sharper in value. That's all this was. Yeah. So this is just multiply for sharpness. Right. This one here was the ax cubed minus by. That's what that one was there. Now to get a by in here, what we need to do is have a node before we subtract the y that we pop in here. Oops, it's not a separate XYZ node. It's just another math node. So Shift-D, put that there. So the y is coming into a multiply node, which I'll call by. And then it's coming from there into the value. And now I have the ability to manipulate the integer, thank you, that is multiplying by y. And then we start getting this without having to use our mapping node over here. Remember, we changed the scale and it was getting us weirdness when it first showed up. But now we can keep the scale, and that's why I was saying earlier the mapping node is not strictly essential. It's just convenient, because we can do a lot of this by manipulating the other variables. See, like that. And that gives you a good sense of what these actual numbers do, which we very rarely learn in math class because we're not supposed to play. We're supposed to work hard and memorize stuff so we can take state exams, so we can get into a good school, however they define that, and then go on to getting a so-called good job so that we can pay a lot of taxes, retire to a cookie cutter home in some vapid neighborhood run by an HOA, and then golf in yellow pants until we have a stroke and die on the green. So, excuse me, munching on pistachio nuts, which are high protein. It's a good snack while I criticize the system. Anyway, so that's lovely. Now we've seen that we should be writing everything or adding to these equations, these other variables. Let's go back to our 10 basic graphs. We just did this one, we did this one. We haven't done this one, but we did an inverted parabola. This is y equals x squared. It's one of the two simplest polynomials. Might as well have it in our toolkit and let that be a review. And for anybody who's just jumping in, you can see that. Before I do that, this one here is our, I need to rename this. This is point slope formula. If I could spell point slope. Slope. I think I was an Arab. Confusing slope and slope. But I am. Half. All right, so we got the point slope formula. We got the cubic polynomial, negative parabola. Yay, hooray for those. Let's put a new one in. And remember, this is a very quick procedure. You go and you add a mesh cube looking down on it. And you create a new texture node tree. It puts in the principled BSDF and material output. We're going to quickly add our texture coordinate system. Drop that on the left. We're going to add after that our our mapping, the unnecessary but convenient in case we screw up thing. Put object to vector. There's that. We're going to add a separate x, y, z and connect those vectors. Bring x over to the base color. Add a math node. Bring it over here and make it multiply so that so that we can sharpen up our image. Sharper image. So we sharpen up our image. That leaves all of this space in between for our other math nodes. And since we already have a math node here in our setup, before we get to equations, we can Shift D and multiply that and drop it in. And we can always do that coming from this. All right, then we need to say, well, what is our equation? And our equation here is y equals x squared, one of the two simplest polynomials. It may or may not change direction depending on its degree. Great to know. It's just for dummies, so this is definitely for me. I'm learning how to be a dummy. So again, adding a grease pencil, or you know what? I can add a text, maybe faster. And I don't have to try to draw with the grease pencil. Let me shrink this way down and put it here. So the equation that I'm going to do is I'm going to do y equals x squared. Yay, good for me. But that's not all I'm going to do. Also, I can't stand it when things are gray. I hate gray skies. So I'm going to make that red. All right, so I've got that, and I'm in object mode. Let me move that up. And now I got to translate that. So let me Shift D and duplicate that down here and go to edit mode. And now what we have to do is transform this to 0 equals, and then it's x squared minus y. All right, but of course, as we said, we always want to put an a in front of the x and a b in front of the y, and then put a c. And is that in fact the quadratic formula? You know, I don't remember what the heck the quadratic formula was, so I'm going to look it up. Quadratic formula. ax squared plus bx plus c equals 0. Yes, it is the quadratic. I remember that from high school. I really haven't touched this since high school, and I'm 62, so will you still need me? Will you still feed me when I'm 64? So that's the quadratic formula. Always put stuff in. They didn't tell us in high school, why do you have to put stuff in this quadratic formula? What? We were learning, you know, y equals mx plus b, and what the heck are this a, and this, was this the same b as the b in the quadratic formula? No, it's not. The c is the b in the y equals mx plus b. Darn it. Crazy stuff. So let us, I'm playing a little mad scientist here. Let us now drop in our other exciting nodes. So we're going to say, did we? Don't have any yet, right? Oh, there, bingo, we did. Okay, so the first thing we're going to do is x is coming out of here, and x is the one that is squared. So in the PEMDAS rule, the exponent carries the day. That's the one that starts. We're always going to start with the exponent. So we'll take this and we will go to power. I got the power. There's power. And that x is going to be squared. Squared. There it is. Our x is squared. And now that our x is squared, like that, our x is squared, we are going to then go to multiply it. It needs an a in there. So to do that, I can take the x squared, which is the first thing, and duplicate that math node and change it from power to multiply. Change the label to ax squared. There we go. So I remember that. If I had to, I could go over here and say x squared, because I'm not going to change that. And then, oops. And then, since I've got that, then it's multiplied by whatever a is. And right now, we don't have any a. So it's multiplied by itself, by 1. All right. Not that it would change. Oh, yes, it would change. Look at that. Okay. So let's put this on 1. All right. Now we have minus by. So y needs its stuff. So I'm going to take this, bring this down here, change its label to just y. And actually, because it's just y, it's going to be multiplied. I'm going to connect y to it, and I'm going to say that this is y. I'm just about by. So I remember. Okay. So by is just a multiply function, and here so far we're multiplying it just by 1. Great. Now the y isn't connected to anything. That's why you're not seeing the x in relation to anything. That's why if I were to multiply this x by stuff, it would just get thinner or thicker, but it's just stuff floating down the x. It doesn't really know what to do with the y information, so I'm not sure how it's drawing a line. Kind of crazy. So what we want to do is connect this y now, which is subtracted from ax squared. So we're going to put in another node, Shift D, put this node in here, and we're going to say, hey you're a subtract node, and who you're going to be, we're going to call you ax squared minus by. That's going to be your name because we're going to try to make it so. We're going to try to observe this formula by saying that y is going to be subtracted from this ax squared. So there's that, and here's what's going to be subtracted from it. Got to break this chain, and then bring this up, and we should now, lo and behold, we have a parabola. But we need that c, and remember I said, if you remember at all, if you were paying any attention, that you can use this mapping node to change the scale, but that we didn't want to. You can just mess around with it. We want to use math inside to do it by doing our algebra. So in here, before we multiply the whole thing to get that sharpness, because remember, if this was really low, like it would be all blurry, which can make great effects if you want. I mean, that's and you can even flip it. Okay. So we have our sharpness here. So we're going to add one more node here, which is going to be the c, because it's going to be ax squared minus by plus c. So here I'm going to make this the whole formula, plus c, where this value is c. And if the value is 0, then it is what it is. It's what it should look like. And that's what we should see over here, right? So it should be at 1, 1, and you're actually looking at this tiny bottom part of the graph, I think. So when you look at it, there's 1, and then your units are always going to be 1, 1, like a whole square to get there, and a whole square to get there. That is what it is looking like. And each of these little boxes is 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10. So this quadrant makes it 1. This would be a y of 1 and an x of 1, and this would be a y of 1 and an x of negative 1. That is what this is showing. It just looks different because we're looking at it from a distance. Because it should be, can't even do that. You're looking at it like that. So that's what we have here, and then we can manipulate c to bring it up or down. That's what c does. It's the y-intercept. Still, like in the point-slope formula, it is still the y-intercept. And we can move these values to narrow or widen. That's by. So that's that one. Or the exponent, of course, does weird things because that would be like cubed. If we wanted to do the cubic function, we could just do the cubic function there. Remember our cubic function? Remember the cubic polynomial? Then you don't need to keep drawing this over and over and over, because this is really a power function. So what I really should say is this is a power function, and not say that one's cubic and one is square, because I could change this to be a square, or to be a cube, or to be a, what is to the fourth? Oh, that's cool. To the fourth power, to the fifth power. Cool. You can learn so much doing Blender like this. The sixth power. Hey, why are they the same? Seventh power. At this point, you're seeing all of these cool similarities. So here we were making a parabola, and we can change things here. If we hit 0 here, now we've multiplied that by 0 and we've eliminated our x completely, and so it's not showing up as a. So we have, yeah, so much fun that we can have in now what is a power function, and I don't need the other cubic polynomial. I don't need that anymore because I have this power function graph. That was prettier because that one had a color mixer. So let's just add in a color mixer here. Color mixer, mix color. Put that in there. Make sure this goes to the factor, and then pick colors that we like red and blue. Oh, that's ugly. Whoever thought of making a flag with red and blue in it? That's disgusting. Red and orange, no, red and green. So Christmassy, so mistletoe. Makes you want to kiss under it, doesn't it? Okay, so neat fun there. Let's continue our journey with our beautiful equations. We've gotten 3 of the 3 of them. We've got the quadratic, we've got the cubic, which really turns out to be the same as the quadratic in our term. We've got the graph of line equals y equals x. Now we go on to the absolute value. Absolutely. Y equals absolute x. All right. So let's grab that and put it in our arsenal. Let us make a... I wish I could just copy all this over. I hate having to keep doing this. And I know that I could do a full copy when I go to make a new thing, but it affects everything after that. So how do I unlink it? What does this do? Delete scene, delete active scene. I don't want that. Yeah, with the new default settings, but how do I copy this thing over? I'm just going to take a hazard for a second that you will indulge me. I want to see how to copy shader nodes from one scene to another. Bing, bing. All right, composition nodes. How to copy shader nodes from one project to another. Control C, put the mouse pointer over the node editor. Really? How to move a node from one scene? If possible, move it. Okay. Link object data. I don't know if that's what I want to do. 2 different scenes. You can copy the nodes from either. Select them with Control C, then paste to the new scene. But you wouldn't let me do that. That's so weird. Control C, Control V. Like, yeah, that's what I was trying to do, dude. It's so weird. Is that like in an earlier version of Blender? Because, like, you know, if I grab all that, and I do copy data, copy full data path. No, what? If I do Control C, and then I go to a new scene, and then I have to add a cube, and then I have to put that in there, and then I go Control V. Oh, it did do it. Look at that. I guess it's because I have to create a material for it to go into. Oh, that's brilliant. All right, then. Nice to know. So this is going to be absolute value. Absolute value. I love the internet. You can learn anything because of generous people who put it online for free. Ah, freedom. All right, so now with the absolute value, what are we trying to do? Y equals x. So again, rather than adding that stupid grease pencil, we'll just add text, and we'll put this up here, and we'll shrink it down, and we'll go into edit mode, and we'll say y equals absolute x. Absolutely. And get out of that. Move that. And for crying out loud, give it a color. Give it a color. Nice and red. Take this, Shift D, duplicate it, rewrite it the way we want to rewrite it, because we always want to rewrite it. This is now 0 equals absolute value minus y, and it is going to be a absolute minus by minus or plus c. Always do that quadratic equation. It's so important for this. All right, so we've rewritten it so that we can get into Blender, and now go back to Air, and we can ignore this, but the absolute value is a parenthetic function in PEMDAS. I suppose that comes first. So the first thing to do is we're not going to use a power function, we're going to use an absolute. Bing. Make sure that we write it as such. So x, or abs x. And oh my gosh, it's already done. Huh. Because I didn't have to write it again. But there's sort of weird things going on here. Like this is a multiply by 1. And yes, we do need that. So you do that first, and then you multiply it. Except that I need to change the label because it's now a times absolute x, right? So we know we just want to keep track of it. And then down here, the by is still the by, but the y value multiplied by 1, because 1 is b, okay, so by is the same. And then this has got to change. It's not ax squared, it's a times absolute x times by. Okay, so that's there. And then we have the a, and it's not x squared, it is absolute value of x minus by? Yeah, minus by plus c. Yeah. Now we can see some cool stuff. Now that we know we can just copy all this stuff and just change it. Ain't that fun? So if we change the c, ooh, we change that y-intercept. We can do an animation. Let's do that. Let's have some fun with this. Let's go to, does it let me change the value? Yeah, you know what? Here's something cool. We're going to go and hit I. No, it didn't work. Wait a minute. 0. Okay. Let's bring it back. You hit, what do you hit? Oh, maybe there's no way to do a keyframe on this value. Can you? Insert keyframes. There is. Boom. Okay. And what we'd also need then is we'd need to make a timeline in here. So where's the shader, text editor, dope sheet, timeline? Okay, we have timeline there. There's my keyframe. And then let's go down to 100 frames, and let's then change this all the way down like that. Except I'm going to bring it back a little bit. I want it to hit, but it's, can't get in on it. There, okay. And then let's hit I, keyframe that. And then when we play it, we go, so now we're getting into Blender math animation, which is totally cool. All right then, so now it's getting really exciting. Now, of course, we can also change the value here. So what if it started out at frame 0 like this? And let's put in a keyframe of that by hovering this over and hitting Y and I, and then bring it down to here. But by the time it gets to here, when it hits the bottom, let's take it and open it up by changing what we multiply the absolute value of x. So like that, and hit I. Oops. Yeah. So now when we play the animation, it goes falling, zzz, whap. Nice. All right, that's pretty cool. Is there another value we can change? Let me go to the halfway point here. There's a by. Oh, that flips it around. Oh my gosh. All right, so that gives an idea. What if we started it down and we were at 1, and we let it go until it gets to here. So we keyframe that. And then when it gets down and it starts opening, we let it open. And then when we get to here, we keyframe that, and then come over to here and then begin to, oh, oh no. Well, that doesn't look good at all. Boom. Oh yeah, you'd have to do that and change this. And change this. Haha. So let's try to do all these. Boom, and boom, and boom. And then it goes, and then it comes up again. Of course, what we want it to do, let me grab these two keyframes and move them over like that. What we want it to do is by the time it gets to here, of course, this has got to be all the way back up at the top. So I'm going to change that keyframe value. And I also want it to be spread in like that. Change that keyframe value. All right, what does this do? It goes, it falls down, it smashes, it hits, and then it goes up. Like that, something like that. Anyway, it gives you some ideas of how coolness you can do with math here. But really, on the first frame, it should be everything is set to 1. And I need to keyframe that and set this one to 1 and keyframe that and set this to 1. I said 1. And keyframe that. Well, what was our other thing? Wasn't it supposed to be, oh, wait a minute. The AX is supposed to be, if this is just the absolute value of X, then the A is multiplied by 1, the B is multiplied by 1. That is true, and the C has got to be 0. There we go. Now we're back to where we began. All right. Our animation is still going to do wacky things, but that's where it starts, so that it looks like that. All right. How cool is that? The reciprocal of X. That's going to be amazing. That should be super fun. Y equals 1 over X and Y equals 1 over X squared both have vertical asymptotes of X equals 0 and horizontal asymptotes of Y equals 0. Symmetrical gives you the same graph. Well, we'll see what it does, right? We'll see what it does. Y equals 1x. So once again, we're going to take our entire node tree, Control, do it, make a new scene, add a new cube, and a new thingamajig, and then put our thing in there. There we go. And I want to differentiate this by changing my colors. Don't like red and blue. I just told you I hate that color combination. Let's do red and yellow. Blue and yellow kind of makes greenish when you're from a distance. All right, then from there, we need to do a text object. Text. And scale it down. And edit it. And we're going to do y equals 1 over x. And we're going to shift T and duplicate that. And in this one, we're going to do y equals 1 over x squared. And take out of that. And to do these two graphs, I don't know if we can do them on the same thing, so we're just going to figure that out. But that's what we're being asked to do here. Y equals 1 over x, y equals 1 over x squared. And so we want to rewrite. So we're going to rewrite this one as 0 equals 1 over x minus y. And once again, it's going to be a over x minus y. And here we're going to say by, and we're going to say plus c. That is what we're going to graph. And the same thing here, but of course I don't have to reinvent the wheel. I can take this over here and say that this, when I edit it, is x squared minus by plus c. Let us start with this one here. And there's our node tree. And I want to then say that that was a absolute x, but this is going to be 1 over x, which is the inverse square root. Is there an inverse? I mean, one thing we could do is just tell it that we're going to do multiply and multiply it by negative. No, you can't do that. It's a power relationship, isn't it? It is a power relationship. It's a power relationship where the exponent is -1. Am I correct? We will see. So that would be called x, or 1 over x, which is equal to x to the -1. That's what I remember from math. You tell me. And then we're going to go, and we've got a and x, which is always nice to have. And then we have our by, which is always there. And then we have our a over x minus by is that one. And then we have a over x minus by plus c. So what is the problem here? Why am I not getting anything interesting? Ah, we do get something interesting if we change c. And this is a case where the scaling might be indeed the problem. So if we scale it, yeah, there it is, see? That's why scaling is sometimes good to have. So that is interesting to me, because we had a over x minus by, so it's minus y in this case, equal plus c equals 0, and c is equal to 0. And when we look at the basic algebra, it looks like that. It looks like that. But if we had set these to 1, we'd really be kind of screwing ourselves, because you couldn't see a darn thing. And then when you take c and you move it, you can't get it in both directions. So you've got to use the scale there, where things get really, really weird. Isn't that interesting? Oh, it's fascinating. I'm absolutely fascinated. You should be too. Yeah, can't do that. So that's -1. So here you've got to kind of decide, okay, I need to change the scale if I want this to be relevant. Interesting how it changes the color, sort of inverse color. All right, so then if you wanted to do x squared, you need another power, 1 over x squared, or you just say inverse square root, but it couldn't be of, oh yeah, just say inverse square root. And then I guess you'd have to see what this does. Well, the square is going to make it just on one side, maybe? Ooh. Well, let me try the other way. Let's go back to multiply and make this -1. Not multiply, what are you talking about? Power. Power. Sorry, so there's the power. This is a power function, and we need to make this 2 and this 2. All right, so maybe more than that. Yeah, okay. If we were going to square this, the x we would have to square, then we would do a power of x first. So we'd add a math node, and this would be called x squared. And then we would square it by making it a power exponent 2. All right, and then we would do 1 over that. So it's 1 over, it's multiplying it, it's 1 over, or it is a power of -1 for the x squared. I think that works. What do I know? Somebody else who's smarter than me has to check up on this stuff. All right, that's kind of fun. For the number that we multiply by. All right. Oh, something's cool there. You can't. Ooh, you can play with that. Oh, you even get to that. Go, why? Why is that? Is that the formula for a parabola? Is it seriously? 1.1 x squared to the power. Yeah, because basically an exponent of 1 means that it is itself. So this is x squared itself. So this is not the inverse. It's not to the negative 1. If I bring this down to a negative 1, that's when I start getting this cool function here. Cool to know. All right, so I'm going to make this negative 1. All righty. Or I make this, let me see if there's a way, if I make this, if I make this, of course, to the 1, then I get that. All right. Cool enough. All right, so what was this called? This was called the reciprocal of x. So I'm doing the reciprocal of x. All right, reciprocal of x. Next, in our basic algebra, the reciprocal of x squared. Oh, well, that was what we were doing on the other. So in here, when I say the reciprocal of x squared, I move this up to 2, and I get that, and yeah, that's what I get. I get the same thing there. All right, so this is actually the reciprocal of x, or x squared. All right, so that's that graph. Fun to know. Now the graph of the square root. Y equals the square root of x. Well, we already kind of have that. Y equals the square root of x. So when we go to square root of x, I might as well just copy it and redo it. Okay, so we're going to do all of this and copy it. We're going to make a new scene. We are going to add a cube. We have our cube. We are going to tell our audience what it is that we're making. So we're going to say y equals, what was it we're doing? Who can keep it in mind? Y equals the square root of x. Y equals square root of x. All right. And do I really have to translate this? I guess I always should. I should always put one of these down here and then redraw it as 0 equals square root of x minus y, and then if I'm being honest with myself, it has to be a square root of x minus by plus c. That is the real way to do it. And now for our graph. Did I not do anything here? I'm going to get rid of these and paste these in and zoom in on them. So let's see, what are we doing here? This one here is going to be square root, not square. So let's change this power to a square root. Equals the square root of x, and then this would be square root, or say a times square root of x, and then this one here is x squared, that's a square root of x. This is, what is this one here? Why do we even have this here now? I don't think we need this one. we should, this is by, and I didn't write this right. This should be, so this here, we are squaring x at the, square rooting x, so this has got to be square root x. That's the first one. Then we're taking a times square root, but we're multiplying it by 1 because we're not doing anything different there. And then we are multiplying by what? Multiplying by 1? We don't need to multiply 1 anymore. So you're gone. Delete. All right, this goes back down to, let's see what it goes down to. by is there. Then we do a subtract the by from there. Then we have a c, and the definition. So why is it looking so funky there? Maybe because we have our scale misset. Okay, well that didn't do anything. Square root, because this is a power and it should be a multiply. Multiply. All right. Still not working. Multiply by 1. Then you're subtracting y. by, because y comes into there. And then you're subtracting that from this. And then there's a no c value. This is a square root. It's the square root of x. And it's doing this weird funky thing here. Why? What is that? It's nothing to do with this one here. Oops, messed up. So you can see the beginning of the parabola there, but why does it get cut off there? What does that mean? Even if I bring this down to 0, if I multiply it by 1, yeah, not so great. Multiply it by 5. Multiply it by 100. No, it's doing something funky that I can't quite get my mind around. There's nothing changed here. Clamp it doesn't help at all. Square root. All right, so really we're supposed to see, if we look at this algebra, of course, because it's only that. Well, stupid me, look at that. It is just that quadrant there, and the rest is yick. It says it stays in the first quadrant. Except for 0, 0, all the points have positive x and y coordinates. The curve rises gently from left to right, and that is exactly, in fact, what we're seeing here. It is doing that, and you can flatten it by changing the multiple of y, and you can change the y-intercept, but when it's set to 0, that's when it's all in the first quadrant. 1 quadrant, 2, 3, 4 quadrants. Okay, so it was working. It just looked surprising that way. See, it's like an ocean of stuff. Yeah, alrighty. That's interesting. And that's what we see. All right, that one worked. So this is the this is called the graph of the square root. So that scene is the graph of the square root scene. All right, we're going to do a new scene then. We're going to take all of this again and copy it. And we're going to make a new scene. And this scene, we're going to add a cube. And we're going to create a new thing, new shader node setup. And we're going to paste this shader node setup in. And we lost our material output, so we need to add a material output because we don't have one. Output, material output, bing, bing. Okay, so that's where we were, but I have a new, save this, a new graph to do. And our new graph to do is the graph of the cube root. That should be interesting. It's an odd function resembling somewhat twice its partner, its square root. So it does that top and then it does that bottom. Let's see what weird colors we get from that. So So this is called the graph of the cube root. Graph of the cube root. Graph of the cube root. All right, so the graph of the cube root should be as simple as, and I want to go back to the equation, but if it's a graph of the cube root, then all I have to do, maybe, oh no, this only has a square root function. I'm not going to use square root then, and it probably doesn't have a cube root. It has an inverse square root, has a square root, but it doesn't have a cube root. So this is a power function, because there's no cube root, and a power function where you make your exponent positive 3, the graph of the cube root. So, no, square root, oh, cube root. So isn't the cube root, is the cube root the inverse? Is that like to the -3? Like if I did that, is that, I don't know what the cube root is. I don't think I know what the cube root is. If I change the mapping, I get that. That's not what I'm looking for, is it? No, I don't think so. All right, so what is a cube root? Cube root is, doesn't even give a formula. Look at that. It doesn't give you a cube root. What is a cube root? All right, is that a formula? What is the cube root? Cube root. Yeah, I know, it's that little square root sign with a little 3 on it. What is it in math? Multiplied by itself thrice produces the original value. Yeah, how do you get a cube root? Cube root. I don't have a cube root calculator. I don't need that. Yeah, okay, to the 1/3. Idiot. Can't remember high school. It's only 50-something years ago. All right, so cube root is 1/3. They're the 1/3 power, dumb butt. All right, so it is a power, but it's not that. It is to the 1/3. Can I just put in 1/3? Can I do that? Ha, yes, I can. Sure can. 0.33333. So that is kind of what it looks like. The point is, the problem of the point is that, you know, if we go back to here, what about that side of it? And it don't give me that. It give me that. And if I change the scale, it just give me that. It don't give me what's underneath here. Now, if I make this negative for whatever reason, negative power, that don't do nothing. All right, so 1 divided by 3. Exponent. So that's 1/3. So it's x to the 1/3 power. Maybe I'm not even maybe I'm not calculating this right. And then you have the a times the cube root. And then you have by, we've got that, so it's just a times cube root x minus by, and then finally you've got c over here. But, I don't really know what to do with this information, because I don't understand math well enough. It is the exponent 0.3. Well, there's supposed to be 2 curves, and I ain't seen 2 curves. So we'll get back to that when I'm smarter. The graph of the exponential function. Y equals e to the x. Oh my gosh. Okay, y equals e to the x. I'm going to try that one out. It's either I have limitations or Blender has limitations, or both, because there's no cube root function in there. But add a cube again. Take that cube, add this Take this away. Go back to our previous scene. Graph of the cube root. Take everything we got there. Copy it. Go to our new scene, which is going to be, what did we say it's going to be? The graph of the exponential function. Graph of the exponential function. Oh, and I lost my terms, so muddle-headed right now. Graph of the cube root. Take all that, copy it, now go to our exponential function. Paste it in, zoom in on it, change the color so I don't get confused. Yeah, blue and blue. Blue and blue is fine. All right, so this is going to be the exponential function, and I wish I could go back and take something like this. Oh, I didn't even write that there. I didn't do any writing there. I wish I could just take anything that I've written here like that and copy it and then go to my next thing and paste it. Oh, you can. So you can and you can. All right. So this was the cubed, which one? Graph of the cubed root. So if it's a cubed root, then it is cubed root. I mean, how do you, yeah, y equals cubed root. I don't even know how to write cubed root with text. Cubed root x. All right, so at least we know that that's what that one was supposed to be. But this new one is the exponential function, and that would be y equals e to the x, I think. Yeah, e to the x. So if it's y equals e to the x, you go e to the x. Y equals e to the x. You want to see this? This is pretty cool. Come over here, and now we have a number, e, and that's going to be multiplied, it's going to be raised to the power of x. Oh, that is really something in there. That's the exponent there. So if the exponent is x, if we take x and put it in the exponent, take that out, then the base is e. And e has a specific value. And they may not have it anywhere, but we can get it. So we say value of e, which is like 2.7, all that, and so on, just like pi. Euler's number. So we go to Euler's number, 2.7, and we put that base, and we put it in here. Oh, it already sort of seems to be doing what we want it to, because then we are multiplying it by a. So this is the a thing, and it's just a times, I should just put this like a times x and just know that that's what the x value is going into. And then we have the a times x minus by. I mean, this is the sort of general formula they're getting here, and then this is ax, whatever manipulation we do to x plus by or minus by plus c, and the by is there, and that should be set to 1 because 1's not happening, and then you can move it with the c value up and down. But as they showed here, when c is 0, I will in 1 minute. And then we have this, it's a curve, but it's not, the only intercept of this y is the y-intercept at 0, 1. Y is 0, x is 1. So if I move this, the intercept's supposed to be down here. Y is 0, x is 1. Oh no, it is exactly what they say it is. My bad. Look at it from here. Let's zoom in on it. Let's make this into 0 so there's no c. And then you see that the intercept is at y equals 1 and x equals 0. And that is exactly what they say here. Y equals 1, x equals 0. That is the graph that we're looking at here. It just seems smaller, and then you can take this up to 2 and change your scale, and then you see it like a little bit more like what you see in that basic algebra there. Okay, so I'm going to come back later and work on the graph of the logarithm. Oh, that's the only one. Can you stay and watch me do the logarithmic? That's the last one. No, because I'm live. So let's just do the logarithmic function and we're done, right? It'll be really fun. Watch how we do it. So you take the graph of the logarithmic function, that's the name of it, and we go into Blender and we say, I'm going to do a new scene. And my new scene is going to be the graph of the logarithmic function. Yay, hooray. Once again, we're going to add a cube. We've really got this down now, real fast with it now. Add a cube looking down on it from the top so that we can see the y-axis and the x-axis. The y-axis in green and the x-axis in red. Then we're going to go back, well actually we'll start from scratch because Anas can see it now. We're going to add a new node system right here. And of course what we're going to put on the left side of the node system is we're going to put texture coordinates because that's what we're doing. We're doing texture coordinates. So we drop that onto the left side. The next thing we add is a mapping node because we're mapping these textures onto that cube and we want to be able to manipulate them. So we take the object and we drop it into the vector. The next thing we add is the separated yxz, xyz. Separate xyz, put it into the vector. And now we have that set up. Now on the other side, remember in order to get things to be non-funky, as you can see if I take this and bring it over to the base color, it is blurry over here and we want to get rid of that blur. Hold on, Nye. So we're going to add a math node. You can have a popsicle. And we're going to put a math node in here and watch that blur disappear as I multiply. Put a multiply here. All right, multiply that value, it becomes nice and sharp. Right, that's our basic setup no matter what math we're doing. Right, those three on the right and these three on the left. Texture coordinate mapping and separated XYZ on the left. A multiply node, a principal. Oh yeah, we also want to get color in this. So just before the principal, the last part of the setup is add a color mixer or mix color and drop that in there. And then we can say to it, oh, that's not a mix color. Yeah, put this into factor and then change the color and say, well, I want pink and I want green. Okay, so I'm set up now to do math. Those are the left side has these, the right side has these. Now for my math, I'm going to drop in a math node. So I'm going to add a math node and drop it in. And the equation that we're working on, this very last equation, is going to be y equals natural log of x. It's a mirror image of its inverse, y equals e to the x, which we just did. So let me copy that, come into Blender, add a, let me look down on this, add a texture, so I text box and move it up and edit it and say, well, what is this graph of? It is of y equals ln x. Now, we want to put that in a form that Blender can work with, so we're going to Shift D and copy that, and we're going to edit it, and once again, as we said, we're going to move the y over to the other side. Simple algebra. We're also always going to be multiplying by a to make it a quadratic equation, b for the y plus c. That is the quadratic equation form that we're going to use. Now that we have that, we go back to our cube and we have to mimic that. So the first thing in the PEMDAS rule is ln x. So x is coming in, but it's not adding, it is natural log. So let's look at this and go to and see, do they have a natural log? They have a logarithm, but there's no natural log. In that case, we're just going to work with logarithms, and then we'll try to find the natural log later because they don't have the natural log. So I'll put the logarithm of it here. And then we're going to, we need the, this is the adding of the c. So this is add, and the c value is going to be 0 for starters. we want to put in a math node and put it for the y, bring the y into the value, and this will be our by. So we're going to make this a multiply, and we're going to say to it that this is by, and then we're going to subtract by subtract it from the x value, and then we're going to put it into there. And it gave us something really weird. Oh, because it's not connected. So subtracting by. All right, and then you get this really weird, that's plus c. So we want to add also a make this a multiply, and then make this 1, and this is ax. So what did we get here? We got something really weird because we are not using natural logs. So let me just bring the scale up and see if that changes anything. If I go 2 here and 2 here, what did we get? What did we end up with? If we look at the basic algebra, maybe we did something. So it's a curve. It goes over there, but this is not the natural log. So that curve is kind of weird. What then if we were to change the base? Okay. So there's the base. I don't know what's going on the other side. That's weird. But changing the base 10. So what did we say that e was? So if I understand it, wait, so natural log, the value of e is 2.7. If I'm not mistaken, then if I put the base at 2.7, yeah, that I think is the natural log. So that would explain why this should look like this. It's just, it's like weird in terms of where it's located. Is that because I changed the scale? If I change the scale back? No. So I'm not sure why the scale, that's what it kind of should look like. But I'm not sure like why the scale needs to be 5 in order to see it. But we are getting closer to understanding that curve with this. And then I'm intuiting that if I take a log, then natural log is a base of 2.7. And I'll just check it finally by going to my friend ChatGPT, and let's see if I can actually ChatGPT. And how would I say, hi chat, how would I understand a natural log? Is it any logarithm with a base of, what does it say? Natural logarithm is indeed a logarithm of a specific base, which is the number e approximately equal to 2.7818. Here's the deal with logarithms in general. They're inverse operations of exponentiation. In simpler terms, if you have an equation like y equals bx, where b is the base and x is the exponent, then the logarithm of y with base b's would give you x. Now, when the base is called natural logarithm, so if you have y equals ex, then its log is x. The e-base is special because it has unique properties that make it useful in calculus, with the rate of change and growth and decay problems. So in summary, a natural logarithm is a logarithm with a base of e approximately 2.7128. It's a useful tool. Yes, so indeed, I got it right. I just don't understand why it produces that on the other side. But that's very, very cool. And what we have now is all of the different graphs that are called the 10 basic 10 basic algebraic graphs. We've translated them successfully into Blender from the absolute value to the cubic polynomial, to the negative parabola, to the point slope formula, to the power function, to the graph of the cube root, to the graph of the exponential function, to the graph of the logarithmic function, to the graph of the square root, to the reciprocal of x or x squared, depending on what we change in our graph over here. If the exponent is 1, then we get that. All right, so thank you very much for watching if you were watching, and always happy to read your comments. And if you want to learn math or teach your kids math, as I do, start looking at Blender. It's a lot of fun.